Okay, stop. Yeah?
Okay, it's working, I guess.
Welcome back to this last lecture on astrophysics. And Alberto will tell us now about black hole binaries. Thank you, Alberto, and I leave you the floor.
Okay, can you hear me? Yeah. Perfect, okay. So last time we saw some of the astrophysical properties of massive black holes. So today we are going to see more how we can simulate them and how do they look like in LISA. So let's start from the beginning. So let's start from how do we simulate. Okay, so we will have to switch on and off, okay. So how do we simulate black hole? There are mostly two main approaches in the literature that you can find. The first one is what is called semi-analytical methods. And the second one is what is called hydrodynamical simulation. In a sense, both these approaches are complementary in the sense that they focus on two different aspects, actually. So, semi-analytical model, as the name says, are indeed analytical. So the idea is that this type of model starts from dark matter merger trees. So the idea is that if you are familiar with the structure formation, so the idea is that you have multiple dark matter halos at like the beginning of the universe, and the idea is that these halos can merge among each other. And in this way, you end up forming halos that are way more massive than the parent one. So this part, the dark matter part, is typically obtained through n-body simulations or again through some analytical formalism. But here the key feature is how do they implement all the baryonic physics. And the key point here is that in semi-analytical model, as the name says, what they implement are indeed analytical prescription. So in a sense, you can view this approach as something more statistical, in the sense that, for example, what they typically do is say, okay, let's suppose that we have a dark matter halo of a given mass. How much matter do we give to this dark matter halo? And this is done typically in a statistical way. And similar process and similar approach is also applied for all the other type of processes. So star formation, feedback, everything is done with analytical expressions that are fast to evolve, but let's say the only thing that they can capture are indeed analytical relations. So the pros of this approach is indeed that since they are just analytical, they are relatively fast to run, and since you are not limited by, as we will see from, you'll not be limited by simulation, they can actually cover the parameter space quite well, which means that they let you simulate a massive black hole from, let's say, relatively light seed, actually the seed that we mentioned last time, so the light seed, up to very massive seed.
Can you clarify exactly what do you mean by simulating a black hole? You simulate its history, its gravitational field, its what?
Okay, so we simulate their history and how they interact with galaxy. So the point is that it's a problem of scale, in a sense. So if you want to look at numerical relativity simulation, then you can really go down to the ISCO. But if you want to do a cosmological simulation, you have to simulate galaxies, so something of the order of 100 kiloparsec. You cannot do that. There is no computer that can actually do that. So what all these codes do, it's basically to take some seed black hole, they evolve it through some prescription. They do not resolve the horizon, typically. Typically, they do not even resolve the accretion disk. I mean, I will show you quickly. But they can give us an idea of how many massive black holes we have, what's their typically masses, and so on. I don't know if I answered your question or not.
So you're simulating the population of
yes.
black holes?
In that sense, yes.
Okay.
I mean, depending on the approach, you might really have a particle that represents a black hole in your simulation. But in that case, it's not like you are solving the horizon or anything like that. The problem with this approach is that since they are indeed analytical, they don't have spatial resolution. Which means that here, I mean, in this type of approach, it's not like you can take 2 points in your simulation and say, these are at a distance of 50 kiloparsec, these other at a distance of 43 kiloparsec. Because again, they are analytical, so they do not care of properties of like the distance of the black hole. Maybe, okay, it's going to be a bit clear when I will discuss also the hydrodynamical simulation. And the second point is, as I said, that they also have analytical approaches. There are also some examples, of course. So examples of code are, well, here I'm writing, okay, maybe this is a bit too small. But for example, a couple of examples are BAC, that stands for black hole, what's that? Across cosmic history. They really have a lot of fantasy here. So across cosmic history. And for example, another one is what is called L galaxies.
Sorry, why is it a const that is analytical?
Sorry, what?
Why can you explain the second const, or the second const?
That's just analytical? Okay. Imagine that you're looking at like the amount of matter that is accreted by a black hole. In principle, you can model it analytically, as we have seen actually in the past lecture. But in principle, if you take simulation, this process is not analytical. You might have fluctuation, which indeed cannot be treated analytically. Or, for example, another effect can be the supernova feedback. So supernova, whenever they explode, they release a lot of energy in the galaxy. And again, you can treat these analytical, saying that a given fraction of the energy is released to the gas, and the gas is heated up. But in principle, if you want to do something a bit more realistic, what you should do is the propagation of energy, angular momentum produced by the supernovae. That is not me. So, let's move to the second thing, to the second approach. And indeed, as you see, is what people call hydrodynamical simulation. So this is actually the more intuitive way that you might have to how we simulate the universe, basically. And the idea is that here what they do is to evolve a box of universe. Typically, again, it depends on the simulation, but typically here we are with a size of 100 megaparsec. So the idea here is simple. Imagine that you have this big box of the universe. There are several approaches, but I think that the most intuitive one is that imagine that you take a big box, you divide it in cells, basically. So here you have the other one, for example. And what you're looking are like the condition at the boundary between the two cells. So between the two cells, what this code do is to resolve basically mass, momentum, and energy. So if you are familiar with hydrodynamics, this is basically Euler's equation. No, this is continuity equation, this is Euler equation. So there are a set of partial differential equations. You end up with a system, and basically you have to solve them at the boundary between two cells. So there are pros and cons of this approach. Pros is that, as you can imagine, since you have indeed like your big box that is divided in smaller cubes, you actually have spatial information. And physics can be, let's say, as complex as you want or as complex as your cluster allow you to run it, this simulation. On the other side, these simulations are heavily expensive, so they have a high computational cost. And here we are talking about the order of 10 to the 7 CPU hours. And the problem is that they have a resolution, typically. So the idea of this hydrodynamical simulation is similar to the idea of surveys, if you are maybe more familiar to that side. So for a survey, you can use you can observe a large portion of the universe, but with like a limited sensitivity. And it is actually the same for hydrodynamical simulation. So you can choose to have a very big part, a very big volume of your universe, but then your resolution is going to be big. Or you can say, okay, let's focus on a specific part of the universe, and maybe in that case I can really lower the resolution of my simulation up to, well, the best one I think at the moment is like 50 parsec. 50 parsec, I mean the galaxy is 10 to the 5 parsec, so I mean you can resolve a galaxy, let's say, but this was really an ad hoc simulation, basically just to push down the simulation. So the point is that since you have a resolution, all the processes that happen below this resolution need some post-process. Basically, the idea is that typically what people do is that when your simulation is over, they take maybe a portion of the universe, of the universe that you have simulated, and they reprocess it a posteriori. So basically, sometimes they need post-process. And as examples, famous ones are, for example, the Lustris, or Horizon AGN. And in order to give an idea of what such a simulation looks like, okay, now I need to switch off. So now what you're looking at is the Lustris simulation. So you can see it starts basically with dark matter halos, these blue points that you see here. And again, if you're familiar with structure formation, you can see that basically you end up creating the filaments. Now it should turn to the gas temperature at some point. Give it a while. Okay. So now, for example, you see that color is changing just because they are changing it in the simulation. You will see some explosion like that, okay? So you remember last lecture when we discussed about the fact that a massive black hole can eject energy in the galaxy, that there is a feedback mechanism between the amount of gas that is accreted and the black hole itself. These explosions, okay, that if you see at the scale happens on a scale of hundreds of megayears, basically represent the amount of energy that is released by the massive black hole to the galaxy. And of course, this simulation goes on. Some point you should also see the change, another change in color that will represent the change in metallicity. But yes, so basically these, okay, so here you're looking at the metallicity, and the idea here is that you can see that, for example, the amount of energy that has been released by the massive black hole has pushed away some of the gas, well, actually I can use this, has pushed away some of the gas away, so it ends up like polluting the intergalactic medium. And yeah. So basically, this is what hydrodynamical simulation looks like, and maybe just judging from the picture, you can understand why it is typically so computationally expensive. And here it goes back to the dark matter simulation. Okay. Any question on this topic?
Okay, I'm sorry if this is a very ignorant question. I feel like it is, but to me, it sort of seems like with semi-analytical methods, it's like you can sort of tune the parameters in a sense where you have, it feels like you might have more interpretability, right? Like if you want to tune different effects to sort of see if you can replicate observation, that might be something easier to do than with hydrodynamical simulations. So is the big pro here really just that there's so much kind of finer physics that we don't know how to model analytically, that like you sort of have to just set it in motion with a hydrodynamical simulation, and there are a lot of effects we can't capture with known equations?
So, I mean, in principle, yes, you should rely on hydrodynamical simulation, let's say, okay. But I would say that even how you model processes inside an hydrodynamical simulation is not completely clear. Mm-hmm. Like the fact that your resolution is limited, it affects your results. And that's actually something that, for example, is not taken into account by a semi-analytical model. Or, for example, other effects are like, for example, people just recently have started implementing cosmic rays in hydrodynamical simulation. Mm-hmm. And, in principle, if you find something that is sufficiently analytical, you can even implement this in semi-analytical model. Okay. You trust them or not. Actually, I have a slide on that. So.
Okay, thank you.
So, as you said, okay, what happens if, we compare different approaches? Because, in the literature, people have, of course, simulated. Okay, here we are. Yes, okay. Because people in the literature have, of course, developed several semi-analytical models as well as several hydrodynamical simulations. So these plots comes from a project of the Astrophysics working group, where the idea is that basically we are comparing simulation, both hydrodynamical simulation and semi-analytical models, with the idea to see if they are really different, first, and second, if we can find some physics processes that are more or less understood by the community. So, what you're looking here is basically the black hole mass distribution. So, mass of the black hole, and here, this label here basically means the number of massive black hole that you have with a given mass. All the lines represent a different semi-analytical or hydrodynamical simulation. And as you can see, they kinda match in the sense that they match typically at low redshift and high masses. So for example, here you can see that there is a good agreement. And that's why, because that's where we have observation of massive black holes. So we know that both approaches, actually all the simulations should recover this type of behavior. But the moment you start going below 10 to the 6, 10 to the 7 solar masses, where indeed we do not have many observation or when you start going at high redshift, well, you can see that basically there are spread of 2-3 order of magnitude or even more. And on the right, what you are looking at is the merger rate. So now we are also talking about massive black hole in binaries. So here you are looking at the merger rate as function of redshift and then number of events. And well, how to say? So they match kinda. So if you're open to interpretation, let's say that they kinda match at low redshift. But the moment you start going at high redshift, well, you can see by yourself, basically there are several order of magnitude of uncertainties. I mean, in a sense, this looks bad, and I admit that. But on the other side, remember that here we are looking at a population that has never been observed. Like, I will also mention this later, it's not like we have many electromagnetic observations of massive black hole binaries. So that's indeed why we are building LISA, to observe this population. And if you go back to LVK papers and you look like at the typical uncertainties in the order of in the rates of stellar black hole binaries or neutron star binaries, you can easily have like 2 or 3 order of magnitude of uncertainties again.
Sorry, I got confused maybe with the, so you're saying that we have more observation for the like 10 to the 10 solar masses?
Yes, you basically have observation here. Because they are very bright, so you observe them.
Yeah, but because I mean most of the like LVK events are much.
No, here we're talking about Here we're talking about massive black hole. Okay, and these are. I mean, the fact that they match here is because they look at electromagnetic constraint.
Okay, thank you.
Okay. No, so sorry, it was clear. Okay.
With all these JWSTs or Hubble and all these electromagnetic telescopes, do we not have, there are a few observations I'm sure we have, right, at these high redshifts. Can we extrapolate based on the selection effects? And do you have a plot of that, like observation rates?
So let me just move one slide.
Or I can wait.
Okay. No, actually, I mean, I can stop here. Okay. So what you're looking here, I mean, probably you have already seen something similar. So this is like signal-to-noise ratio as function of redshift and total mass of the binary. So this gives you the idea of the typical signal-to-noise ratio with which we can observe basically massive black hole. So to go back to your points, where James Webb and like high redshift observations sit. So high redshift observation, well, if they are really high, I mean, it means that basically you are taking something of 10 to the 9 solar masses at like a redshift, like here, something like that, between 6 and 8. So in principle you can, but the idea is that this object has already like passed LISA band, so it's difficult to give an idea of the merger rate that you expect from these events. You have a set of electromagnetic observation in this area here, so again, low redshift, and this is where also all the simulation matches. If you take results from James Webb Telescope, I mean, on that I cannot say completely for sure because like it's very recent and there is basically one paper every few days about James Webb observation. But the idea is that they should sit more or less here. So if we take a James Webb observation for what people have thought so far, so a more massive black hole at high redshift, this is actually a good news for LISA because we might have more massive black hole at high redshift, which means that in terms we might have more mergers. The direct connection between the two, I would say, is not so trivial, honestly. In principle, what you can do is, to tune your semi-elliptical model or your hydrodynamical simulation in order to reproduce the James Webb results, and then you look at what you expect in LISA. That is something that you can do, of course. But in principle, you're assuming the same physics. And honestly, I would say that we don't know, since it's a complete new set of data that we have, so there is still a lot of investigation necessary to understand James Webb results, I will say. Okay, so with that we move to massive black hole binaries. So you already had lectures on data analysis, so I'm not going through that, and I will focus on a particular information that we can get from massive black hole binary. That is the sky localization.
Can I ask a quick question?
Yeah.
Amongst the examples, I've heard of this Firebox and I've heard of Illustrator. Are these like what, or those two, for example? What distinguishes them?
It basically depends on the type of physics that they implement. So, type of astrophysical processes, like maybe some of them has cosmic rays, some other don't. How do they implement that? Because there are different prescriptions. And for example, it also changed, I think, the resolution. So I don't remember honestly the values between the two, but okay, let's say that maybe one has a resolution of 1 kiloparsec, the other of 5 kiloparsec. But again, this depends on like the error volume that you have, and most importantly on the cluster that you have to back you up. But in principle is that, of course, I mean, since these are very expensive, it's not that people are running the same hydrodynamical simulation that has already been run. So typically they try to focus on, let's say, complementary portion of the parameter space in order to get a bigger view. Of course, this makes comparison a bit more challenging, but redoing just the same simulation is not something that people do. It's not like they're redoing the same simulation to have more statistics. So let's talk about the sky localization of massive black hole binary. And to that, I will refer to a paper from Sylvain Marsat with archive 2003.00357. Okay. I guess you are all familiar with the idea of LISA that is orbiting around the sun, so I'm not gonna draw a picture or anything else. But the idea is that when you look at the sky localization of massive black hole binary, you get information mostly from two effects. So the first is, as you can imagine, the time dependency. So the fact that, LISA orbits around the sun, and since it's orbiting, it's basically you have sort of a Doppler effect, and this actually helps you in localizing the system. The second is the frequency response. Sorry, let's call it frequency dependence for consistency with the first one. What does it mean? So if you're familiar in the context of LVK, we have, if you take the typical wavelength of gravitational wave signal that we observe in LVK, we are in what is typically called long wavelength approximation, which means that the wavelength of your gravitational signal is typically much longer than your detector. So in a sense, your detector is kind of a particle, a point particle that observes the passage of the gravitational wave. However, this is not true anymore in LISA, and you can see it quickly. For example, if you take a gravitational wave of frequency 0.05 Hertz, you end up with a wavelength that it's of the order of 6 times 10 to the 9 meter. And again, if you're familiar with LISA, its armament are of the order of 2.5 times 10 to the 9 meter. Which means that, these wavelengths start being comparable with the armament of LISA, and indeed you have this frequency dependence that actually help you to improve this localization. So if you take a massive black hole binary, this is like the plot for the signal to noise ratio, but again, let's suppose that you simulate massive black hole binaries, you compute the Fisher just to make things easier, and you know what Fisher is because Stas told you, okay? What you end up is something like that. Do you see it clearly, or do you need the light from the fair? Okay, perfect, okay. So what you're looking here is the sky localization again, redshift and total mass of the binary. And, well, colors corresponds to different sky localization value. And, for example, you can see that if you are around 10 to the 6 solar masses, we have like an average sky localization of the order of 0.4 square degree up to redshift 1 and something. And, well, here we reported 0.4 and 10 square degree, just because this is like the field of view of a couple of telescopes. I'm just going to mention them, but like this is Athena and this is the Vera Rubin. So in principle, this is what you get. And you can also do something that is more like more accurate. So you can look at MCMC. And I guess that Stas also mentioned that. It's basically Bayesian analysis. So for example, here you're looking at latitude, longitude, and then you basically end up with a nice posterior distribution for this sky localization. That's happening most, okay.
Sorry, maybe a naive question back on the other slide. So it looks like LISA is expected to be much more precise maybe than LVK. Is that true? And I would have thought it would go the other way because of this argument.
Say it again, sorry.
Can you compare this to LVK maybe for someone that I don't know the numbers in my top of my head? Is this good or is it bad?
Well, I mean, I would say that if you take the three networks, the networks with three detectors, and maybe if you put LIGO India, then you start building a network, and that should be, I would say, maybe better than what LISA can do, though I have never seen estimate.
Okay.
But I would say that maybe at the current status where there are just the two LIGOs, LISA is slightly better.
Okay.
Again, it depends. I mean, it's difficult to give you an answer just based on LVK because it depends on how you observe the signal. So I think that the first neutron star events, what was this localization? 60 degree, if I remember correctly, or okay.
17 degree. Okay.
Okay.
Yeah, okay.
So in principle, that's okay. Maybe LISA, I mean, the prospects for LISA now are better than what LVK is doing at the moment. But in principle, LVK you can upgrade it while it's on the ground. So it's difficult to compare.
So is the fact that this looks slightly better maybe than LVK, is this due to this frequency dependence thing? Because I would have assumed that this was a hindrance, not a positive point, but it sounds like, it looks like...
Well, if you know how to treat, no, it's a positive.
Okay.
But it's not just this one. Okay, so you have the time dependency. That is something that it doesn't happen in LVK. Well, you have your signal that lasts in bands 1 so okay, basically stationary. And actually, I will comment on the same things for LISA. And plus, you also have the fact that if you look at the typical signal-to-noise ratio, typical signal-to-noise ratio are larger. And okay, there is not like a one-on-one correspondence between sky localization and signal-to-noise ratio, but 0 order of magnitude, let's say there is.
Yeah, no, the plot. The
previous one?
Yes, this plot. So am I correct to understand that when you have larger, when the total mass is higher, then the frequency is lower, so you lose this frequency dependency. So you lose it. But when you have even higher mass, why can you have a better resolution in sky? So basically, going from 10 to the 6 to 10 to the 8, it seems that you have better resolution.
Here?
Yes.
Yes, but because here you have both. I'm going to say this quickly, but here typically you have both the motion of LISA and the high frequency response of the detector.
Wait. Okay, no. I think I misunderstood the plot because I thought that actually it's better in the wings than in the core, but actually you have better resolution in the core, right?
No, yeah, sure. Brighter color corresponds to better sky localization. Okay. And actually, going back to your point, so let's take an example. So let's consider a system of 10 to the 8 solar mass, and let's see what happens for this type of systems. So, as I said, let's consider a massive black holes of the order of 10 to the 8 solar masses. So I'm going to draw the sensitivity, but of course, I mean, it's just to be more like a conceptual sketch. So here you have frequency. Here imagine that you have your PSD. Here is LISA sensitivity. Again, order of magnitude, I just want you to get the idea. So if you take a system of 10 to the 8 solar masses, you know that for this type of system, what we observe is typically merger and ring down. Because maybe you have seen during one of these lectures, the ISCO frequency scale as the inverse of the total mass. So the more massive a black hole is, at lower frequency this merges. So a system of 10 to the 8 solar mass with look in LISA as something like that, basically. Well, this peak here is the merger, and this one is in this case, the ring down.
So are both black holes 10 to the 8? Sorry.
You can take total mass, but yes, it's the same. It doesn't change that much. Change a factor of 2 if you take a symmetric mass ratio. So the point is that since these systems merge at low frequency, what do you have? Well, first, you have that the wavelengths of this gravitational wave signal will be much longer than the element of LISA. So you are back to the point of the long wavelength approximation. So LISA, again, is seen as a point-like detector by this type of gravitational wave. And the second limitation is the observation time, that you can do the proper computation, okay, but for this type of object is of the order of hours. And in a few hours, you can basically assume LISA as a stationary detector, in the sense that it's not moving. And you end up with... okay. It's basically stationary. So in this sense, you end up with a situation that is quite similar to LVK. So something that is long wave, something that gravitational wave wavelength that is much longer than the arm of your detectors, and a short duration signal. And so what happens basically for this type of system? So you end up having what we call the multimodal events. So here you are looking at a system whose sky posterior distribution is actually okay. So here you are looking at a system whose sky posterior distribution is actually multimodal in the sky. So here, for example, you can see, this is where the binary was actually simulated, and this is actually the result from Fisher, but you can see that the MCMC recover another position in the sky, and even worse, you might have 8 different spots in the sky. Now, why does this happen? Here I have to ask you to trust me, in the sense that if you want the full derivation, you can find it in section 5b of this paper. So if you want, you can look at that. I'm not going to do that just because it's like a combination of spherical harmonics and pattern functions, so it's just algebraic substitution. But the idea is that these two information helps you breaking degeneracies. So whenever these two information are missing, you end up with degeneracies. And for example, it has been shown that one of the degeneracy, that is actually this point here, is due to the fact that if you take your standard binary, so characterized with longitude lambda L, latitude beta L, inclination I, polarization psi, and phase out coalescence phi, you can end up with a change of coordinate that is like lambda prime equal to lambda L, beta prime L equal to minus beta L, psi L prime equal to pi minus psi L, inclination prime that is equal to pi minus inclination, and phase prime that is equal to phi. So basically you can find a change of coordinate of your extrinsic parameters that produce the same gravitational wave signal in your detector. If you have this information, this degeneracy, this transformation is broken. But whenever you don't have this information, this type of degeneracy is present. And that's why you end up with 2 or like 8 different spots in the sky. if you want to think it in another way, basically assume that there is your binaries in this way. Okay, it's coming from that direction in the sky, so you can reproduce the same gravitational wave signal in LISA, taking a binary that instead of being in that position is reflected respect to the plane. Polarization means that instead of starting in this way, imagine that the binary is face on, so it's pointing at you. Polarization means that instead of starting like this, you start like this. That's just polarization. And inclination means that instead of looking at you, so face on is face off. This is just a change of variable, completely extrinsic, that at the end up producing this sort of degeneracy. And indeed, we can also look at this at how this is distributed in the parameter space. So here you're looking at chirp mass and redshift. And here, like the blue circle corresponds to system with just one mode, square corresponds to system with 2 modes, and then you have a system with 8 modes, basically. So the plot that I show you on the right. This is for different formation channels of massive black hole binaries, so that's not important. But for example, if you look at here, you can get an intuition of why this type of degeneracy increases. So, for example, if you take one of these blue points, you have that for these blue points, you can observe it for a sufficiently long amount of time because they are relatively at low mass. Okay, low mass 10 to the 5, but okay, still technically low mass for LISA. So, which means that you have the orbital motion of the detector, and also they merge at a frequency that is high enough in order to have the frequency dependence. If you start moving at the same mass but a higher redshift, your total redshifted mass increase, which means that your merging frequency will be lower. So again, that maybe in this case you can still get some information on the time response of LISA, because again you are observing the motion of LISA. But for example, in this case, since they are merging at lower frequency respect to this one, you are losing the frequency dependence of the detector. And for this type of system, as I've told you, basically, you can observe them for a very short amount of time. You don't have the frequency response to the detector, so you end up with this type of degeneracy.
What do you mean by stating that we do not have access to the frequency dependence? Because when I have a time series, a signal, I always think of, okay, let's see what is there in the frequency domain. And I mean, if I find the signal in the time domain, I don't see why I shouldn't be able to see it in the frequency.
No, it's not that you don't have a signal in frequency. It's that your signal in frequency merge at a frequency that is too low respect to when this long wavelength approximation breaks.
Okay.
Want me to repeat or?
Yes.
Okay.
I mean, not sure if I understand why this causes a degeneracy.
Because technically, I mean, this is like an additional information. So the point is that if your if the wavelength of your gravitational wave signal is of the same order of like your arm length, okay. Your arms, the arms of your detector, do not see anymore just like one big wave, let's say. No? Imagine that this is the arms of LISA. So if you're taking something that is with a wavelength that is much larger, you're going to see something like that. Okay? If you take something that is much smaller, you might observe something like that. So if you are, I mean, this gives you additional information, basically. The fact that it is not anymore a point-like detector, but it has a structures. So, okay, in another way, thinks that there will be lasers going along, from one spacecraft to the others. And the way the time delay between the spacecraft will work depends on this type of information. Not yet convinced.
No, but okay.
Okay, we can talk later. Okay,
Yeah.
we talk later. Back.
So you want to see a time evolution. You also want to see a frequency evolution of the signal.
Yes.
So in a time frequency map, you want it to be not flat. You want it to be chirping. That's what you're telling me. The more chirpy the signal is, and the longer it stays within the time frequency, the better is the resolution. The fewer modes you get in the PE. Is that a generalization that's not true? Is that a statement that's not true?
Let me think.
So you want it to span frequency, but also time?
I mean, in principle, yes, okay, but I would say that the idea is a bit different from galactic binaries. So, because in any case, also for a system like that, you can see some frequency evolution. Because, for example, you see the frequency evolution from merger to ring down, so you can see like the frequency evolution of the signal.
But it would stay for a short period in your...
Yes, technically, yes. It's going to stay
So
for
you
a
lose
very
the
short
time-
amount of period.
Yeah, so you get just a blip rather than a long...
Yes, exactly. In
Which
this
is why
case,
10
yes.
power 6 is so well resolved, right? Because it stays for such a long time.
Exactly. So, yeah, this type of system, I mean, I'm not going to say that they will look like glitches, but kind of. So, basically, you will have a very
Gotcha.
short signal.
And if it's super small, like below 10 power 5, then the signal's almost not chirping that much in frequency?
Honestly, I don't remember if it
'Cause
is
they
like an effect of the population of massive black hole binaries. Like, we don't have points there.
Okay.
I don't remember, honestly, that. But in principle, no, it should still be chirping. The point is that typically when you go at 10 to the 4, let's say when you go typically at 10 to the 4, you don't have any more the merger in LISA. So
It's
what
an
you observe
SNR
is the
thing.
spiral, and then the merger happen outside band. You can get some information because in that case you still have like the orbital motion of LISA because you observe the system in the spiral, but you lose a lot of information because you are not observing the merger ring down. And typically what people have found is that if you put higher harmonics in your gravitational wave template waveform, this actually helps you a lot in breaking degeneracies. So for example, also for a 10 to the 4, like spins are typically not constrained because you constrain them when you are close to merger.
And last question, which is, can you make a similar plot for mass ratio? Does it depend? Is there a dependence on mass ratio? Because you just mentioned, I would have thought that higher mass ratios would have better, fewer modes.
Again, I would say there is a trade-off between mass. When you play with mass ratio, of course, when you want higher harmonics, yes, you need something that is unequal. But remember that if you go really unequal, then you start losing signal-to-noise ratio.
Okay. Gotcha.
Again, it's a trade-off.
Okay.
So the final point that I would like to mention here is that, as you see, this type of multimodality is, actually, there is something else that I want to show you. Okay. So this type of multimodality appears also if you take like a standard system, let's say someone that ends up with a single mode in the sky, but you look at it during the spiral. So here you're looking at a single system, and all these contours represent the sky localization 40 hours before merger, 2.5, 7 minutes, and post-merger. So basically what you see is that, of course, 40 hours is basically detection, if I remember correctly, for this system. So sky localization is, the entire sky, basically, okay? Then at 2.5 hours before merger, you see again the appearance of these 8 different modes in the sky. And then like 7 minutes and post-merger, you can see that at the end you end up with a very nice and well-localized region. So, if you want a message from that is that all the systems appear multimodal during the spiral, which actually it's a serious complication whenever you want to look for electromagnetic counterpart, as I will tell you shortly. But if you take the correct range of masses, actually you end up with a nice sky localization of 1/10 square degree, let's say. So there are. Okay. Sorry. Okay.
Super naive question, but in practice with LISA, how quickly do we get information? Like, how long do we have to wait until we, for example, I guess it's instantaneous. But
So if I remember correctly, LISA is supposed to send data every 8 hours. Okay.
yeah, but so there's no chance to help. Yeah.
It's a hybrid. I mean, that was the idea. That let's say you observe a merger happening just within spiral, and you're able to predict that the time of coalescence is going to be around this age. Then you get a hybrid. Like we just reserve the band, and we get live updates, like minute by minute. Or
Sure. But there's still some delay, I assume. No?
Yes, there is delay
Is it
between
like
the
order of
merge.
minutes, seconds?
I would say minutes.
Okay. Because then there's no way we can tell like EM telescopes, oh yeah, look in that direction, right?
Yes, so moving to multi-messenger now. There is a question over there.
You can also have the generacy for the distance. And in that case, like distance and inclinations.
Okay. I mean, yes, that is the typical degeneracy that you expect between inclination and luminosity distance, but it's not like you will have luminosity distance that are bimodal or something like that.
Okay.
No, that is quite safe, let's say.
And in that case, higher harmonics are the most useful information that
Yes.
can break the
Yes.
degeneracy.
So let's move to multi-messenger. And if you are not, if you're not working in the multi-messenger field, of course you might ask why people are so obsessed with that. So why is so important? And the reason it's that the additional science that we can do combining two detectors is typically beyond the science that a single instrument is designed for. Just to give an idea, for example, if you combine, the idea of doing multi-messenger between LISA and other electromagnetic observatories is that, with that you can test astrophysics, for example, and we cannot just test astrophysics, but we can test it at extreme scale. So, for example, in this case, imagine that you are observing the merger of a massive black hole binary. There is some gas around it, and if you combine the information on this localization, and if you point sufficiently quick this localization, you can get like the emergence of a jet, basically. And other reasons are, for example, cosmology, but I will not talk about it since Danny will talk about it tomorrow. And something else, for example, is also fundamental physics. In this case, for example, what you can do is a propagation test. So you can test if your gravitational wave propagates at the speed of light. But the general idea is indeed, if you put together two instruments, you can do more than what a single instrument is designed for. Let's see. Okay, so before we move on, I will just gonna mention briefly how multi-messenger works in the context of LISA. There are several ways to do that. I will not go into details, but I will just mention it quickly. So, okay, let's write. So there are basically three ways with, to do multi-messenger in the context of LISA. The first one is pre-LISA EM searches. So this is actually a very active field of research. The idea is that you can look at surveys like LSST, and you are looking for modulation, some sort of modulation in the electromagnetic emission. And the idea is that if you observe some sort of again, here there is time, let's see, and here there is the flux at a given frequency. If you observe some sort of modulation as function of time with a given periodicity, this modulation might be produced by, if you imagine, a couple of black holes orbiting around each other, and each one of them with its own circumbinary disk. So the idea here is that, as I said, people look at surveys. They search for modulation. Like I know people that have done this in the context of LSST, that they're doing that in the context of LSST. And the idea is that if you can get some sort of modulation, they say that if you are lucky enough, maybe the binary might even merge in LISA. So this kind of reverses. So first you detect the electromagnetic counterpart, and then if you are lucky enough, you get the gravitational wave signal. Or otherwise, if you detect this type of modulation for enough system, then you can put upper bounds on the number of mergers that you expect. Second way is archival searches. Here we are moving at the time of LISA. So let's suppose that, for example, I just finished. Okay. So let's suppose that, for example, we were not able to point our telescope sufficiently fast in order to detect the electromagnetic counterpart, but LISA has given us like an error box, so we know more or less that the signal is here, where, for example, here you have an uncertainty due to the sky localization, delta omega, and here you have an error on the luminosity. Well, actually, what I'm doing, okay. Here on delta omega, and here, for example, you have an error on the luminosity distance. What you can do is do archival searches. So you go back and you look at all the surveys or telescope that has looked in that particular area of the sky, and you see if there is some sort of flare or something, whatever, that might indicate the presence of a binary. In principle, this is exactly what happened with the first neutron-star merger. So they saw a flare. They went back to archival data. They saw that the flare was not present, and okay, there is the counterpart.
So a quick question on the first part.
Okay.
Yeah, surely. I mean, didn't do astrophysics much, but surely there's like thousands of things in the universe that could create such a modulation, or is it purely
a periodic modulation that stays like that for years?
Okay.
I would say no.
Okay.
I mean, I would say it's. So if you're looking for transients, like something that it's like electromagnetic emission on a very short amount of time, then it's a complete mess. I will actually show this later. Later. But a modulation, no. Typically, something like that, it's a bit difficult. And the third one, sorry, it's what is called target of opportunity, so TOO. And it is actually maybe what you have more intuitively in mind when we talk about multi-messenger. So LISA detects an event a few hours, 1 day before the merger, whatever. We send the alert to electromagnetic telescope. We ask them some observational time to look at the time of merger, and eventually we hope to see an electromagnetic counterpart. So this is what is called target of opportunity. Okay, so now that we have seen this, what type of electromagnetic counterpart do we expect from massive black hole binaries? So an important point is that at the moment, we have no electromagnetic counterpart from massive black hole binary, in the sense that, and it's not because we don't have massive black hole binaries. So at the moment, there is like no transient AGN-like emission that has been observed unambiguously. So we see, for example, AGN turning on and off, but there is no like an AGN emission that you can clearly say, this is like there is underlying that emission there is a merger. What we have in the literature is what people call dual AGN. So these are the situation where you have two massive black holes. So, okay, you have two galaxies. There is a massive black hole in the center of each galaxy. The galaxy has merged, but the two massive black holes are still far from each other. So in this case, you can, for example, observe the two radio jets, but if you take the typical separation, these are separation between 1 parsec and 10 kiloparsec, for example. So they are way, way too far from LISA. The second is what in the literature you can find as binary AGN, and here, I mean, it's more rare sources because they have a typical separation of 1 parsec, well, smaller than 1 parsec. So the point is that we have this type of emission. Well, here I don't know if there are like confirmed observations. I know that there are candidates for that, but yeah, here there are also observations. So here the main point is, okay, we have this type of observation, but we have this observation where when massive black holes are still far from each other. So the question here is, can we take this observation and push them down to the merger, or at merger, since we are, I mean, at merger there will be two massive black holes, two objects of 10 to the 5, 10 to the 5, 10 to the 6, 10 to the 6, or, I mean, orbiting at a fraction of the speed of light. So can we take the observation that we have and push them down to merger? At merger, we will see the same things or not? I don't know the answer for it. And the second point is that there are a lot of uncertainties on, let's say, all the astrophysical properties that are connected to massive black holes. So, for example, spectra. So, what type of spectrum we should expect from a massive black hole binary merger? Or, for example, what type of obscuration we should expect from this type of system. Obscuration here refers to the fact that last time we saw that gas is accreting on massive black hole, but the same gas that is accreting is also absorbing a fraction of the radiation. So the point is that we have this type of relation, also bolometric corrections, okay. But the point is that we have this type of relation for the system that we have observed electromagnetically so far. So for something that is very massive at high redshift. And it's not clear at the moment if we can basically push them, if we can also apply them for system of 10 to the 4, 10 to the 6 solar masses. So since there are no observational constraints, as you can imagine, we have to rely on simulation. And here I'm going to split the topic in two. So basically what we can do pre-merger and what we can do post-merger. So pre-merger, we mostly have to rely on GR-MHD simulation, that stands for General Relativity Magnetro-Hydrodynamics. Okay. And if you look at this type of simulation, I'm just gonna sketch them, of course. So the idea is that typically, if you look at this type of simulation, you have the two black holes here. You see that the massive black hole excavates what is called a cavity in the circumbinary disk, and you typically see stream of gases going from the inner edge of the circumbinary disk to the massive black hole. Actually, to make also things easier for you, okay. So, so I don't have to draw it. So for example, here you're looking at a set of hydrodynamical simulation before the merger. So what you're looking here is that, for example, here you can see that there are the two massive black holes. Okay, sorry. Let me explain the plot before. So here you're looking at y-axis. There is time. So this is deep in the spiral, and this is at merger. And columns corresponds to different mass ratio. Just focus on like this column, just to make things easier. So you can see that during the spiral, you can see that the two massive black holes that are here, they are, well, in this case, this circumbinary disk is not perfectly symmetric, but okay. But you can see that there are a couple of mini disks. This is what This type of disk is what people call mini disk, just to distinguish them from the big circumbinary disk around the massive black hole. And the idea is that the mini disk, the stream of gases, and the circumbinary disk, they all emit at different wavelengths. So, for example, the circumbinary disk will typically emit in optical, stream of gases will emit in UV, and then you have the mini disk that typically they are expected to emit in X-ray. So if you look at this, you can also see that there is, what we expect from this scenario. Imagine that your simulation is going on. So we expect two features typically from this type of process. Where do I go? Okay, here we go. So the first one is that we expect a modulation of the electromagnetic counterpart. Why? Well, intuitively, you can think this as a Doppler effect. So imagine that you're looking at the binary edge-on. So you have the two black holes in this case, and they are orbiting around each other. So you have that one of the black hole is receding from you, the other black hole is approaching you. And this basically leads to a modulation of the electromagnetic counterpart. And the second that, this is not, you cannot see this. Well, actually, yeah, you can see. You can see that as we approach the merger, basically the two mini disks gets depleted. And at the end, you end up with a merger that, basically it has no electromagnetic counterpart. If you want to have an intuitive idea of why this is happening, well, the idea is that if an object moves too fast respect to a medium, it will basically leave the medium unaffected. So as long as black holes are relatively, let's say, low, they're relatively slow, they can still get some gas from the circumbinary disk. But as they approach the merger, they start moving faster and faster. And this means that they decouple completely from the circumbinary disk. So this leads to a drops of the electromagnetic counterpart. And if you want to have, a clear idea of the picture, you can look at this one, at this plot. So here you have luminosity as function of time left before merger. Different color corresponds to optical, UV, X-ray, and like the volumetric, the total luminosity. Okay. So for example, if you look at X-ray, the green curve, you can see that you have this sort of modulation, and then as you approach the merger, you basically have a sudden drop of few order of magnitudes in the luminosity. So in principle, both these. So in principle, both these features are unique feature of the presence of a massive black hole binaries below. Sorry, but the point is that there are also problems if you want to detect this type of emission. And well, the first one is that I will put it as under cons. So the first one is that, as we have seen, the sky localization is multimodal. And the second is that detecting this type of modulation requires a long exposure. So in principle, you have, if you trust the simulations, what these simulations are telling you that you have a couple of features that you can look in your electromagnetic data to find a counterpart to a massive black hole binary merger. On the practical sides, there are a couple of problems. So the fact that sky localization is multimodal, and the fact that in order to detect this type of modulation, you basically need observations that are very accurate, one after the other, basically. So it's possible. I say it's something that maybe we will do, but it's difficult to get an electromagnetic counterpart because, well, it's a difficult scenario. If we go after merger,
Why don't we see any change in the optical luminosity in this plot?
Because because the optical comes from the circumbinary disk, and that is not affected by the merger.
Okay. And BOL stands for what?
Bolometric. So bolometric luminosity is the luminosity that you produce if you integrate across all the electromagnetic spectrum. It's like a measure in astrophysics of like the total luminosity that is produced. So if you go after merger, the situation is slightly, I would say, different. So after merger, what we have, it's typically the following scenario. So you have a remnant black hole that is sitting at the center of its circumbinary disk. And here you have two scenarios. The first one is that the black hole is kicked. So at merger, the remnant black hole receives a kick, and the kick push the massive black hole, the remnant massive black hole, in the circumbinary disk. In this way, you can get, well, the massive black hole will go through a region where there is gas, so you can get again some sort of accretion and an electromagnetic counterpart. The second possibility is that maybe the black hole do not receive a kick, but if it does not receive a kick, you expect the black hole to start accreting again. Why? Well, because if you remember what we discussed in the last lecture, I mean, if there is no electromagnetic radiation and if there is gas around the black hole, typically you expect the gas again to start accreting on the black hole and to produce electromagnetic radiation. The cons of this approach is that typically it's not clear when the electromagnetic counterpart will emerge. So well, actually I can write when the end counterpart emerges. Because like if you take both scenarios, even if the remnant black hole receives a kick and is pushed in the circumbinary disk, this will take a while, of course. And same like if you assume that the gas will start accreting again. How much? Again, it depends on your configuration. It can be days or weeks, which make, of course, the association between the gravitational wave events and the electromagnetic counterpart very, very challenging, of course. Question on the back.
Yeah. So if I look at this figure, it's very clear that the clearest signal will be in the X-ray band, right? Because the other bands are changing rather less around the merger time.
Yes.
So would this be a strong argument to have an X-ray telescope in the sky at the same time as LISA launches?
Technically, that's the idea of Athena.
Yes.
So, I mean, LISA was the third flagship mission from ESA. Athena was the second one, but budget of, well, LISA was 1.7. Athena is still, I guess, under discussion, okay? But that's why they want to have both LISA and Athena at the same time. Yes, that's why, that is one of the arguments behind having both. Yes.
So now I'm starting to not understand the point of the L2A, which is a shame because that's what I do. So I would really hope that there's a reason I'm working on this. But because it looks like post-merger, we don't expect a very loud signature. Maybe. So is there?
What?
Because it's useless if I tell you after the merger, you've missed out on all those periodic signals. You've missed out on all of those interesting physics that you could have tested. You do perhaps get that X-ray thing if I'm able to give you, if L2A is able to give you a good sky localization. But is that the, so we can, that's the only question we can answer. That's the only thing we can probe, I guess, post-merger. Because prior to merger, our sky localization is so bad, right, as you've just shown. So, so do you need it to be low latency? Because after merger, you're saying we have weeks, perhaps, until the black hole, being kicked, enters into the accretion phase again.
Yes, we need low latency, so your postdoc is saved, I guess.
Thank God.
But so the point is that, yes, sky localization is multimodal in the spiral, but again, it depends from the type of system. I mean, you need low latency, but for example, if you take a 10 to the 5 solar mass at redshift 1, if I remember correctly, you should be able to detect it like even 1 month before merger. So with that, we have plenty of time to start looking for that. So, and the sky localization for this type of system at 10 to the 5 is typically expected to be good because you have basically the orbital motion of LISA. So I would say that maybe low latency is not the best if you take a 10 to the 8 solar mass, because then in that case, yes, you really don't have time. And the only thing that you can do is to point a posteriori. But for light system, yes, definitely we need low latency because in principle, you can still look at the sky localization before the merger. It's going to be multimodal, it's going to be larger, but you can still give it a chance. And moreover, we need also low latency because also we need information on like when the massive black hole will merge, because at that point, okay, maybe that will be more a political discussion in the sense that the ESA will have, I guess, to collaborate with the other telescopes in order to get some observational time. And maybe it's going to be difficult to get observational time during the spiral, because if you go to an observer and you ask them, can you observe this sky localization of 100 square degree? They will tell you no, probably. But if you give them a projection on the sky localization that you will have at merger, plus a reasonable error like on the time of coalescence, that is a game changing, basically. So in principle, you still need low latency. There is a question.
Are there different astrophysical objects that could mimic a similar emission in some part of the...
Yes. So can I move to the other slide?
Nice.
Yes. Well, no. I mean, wait. Okay. So the modulation and the drop, I think it's quite a unique feature of massive black hole binaries. This type of like rebrightening, by the way, I forgot to say that this type of accretion after merger is called rebrightening because you expect the massive black hole to go dark, and then you have a rebrightening, okay? So this type of rebrightening, it's a bit more complicated to mimic, but not impossible, in the sense that imagine that, for example, you are looking at an AGN, and AGN has variability, basically, of years. Depends, okay? It can be shorter, but okay. So let's suppose that you're looking at AGN that has a variability of years. So maybe you are getting it, let's suppose that, you have time, flux. So let's suppose that your limiting flux for your instrument is like the dashed line. And let's suppose that before doing the lead observation, the AGN that you were looking at was dormant. So in that case, it was like, or maybe not dormant, but it was emitting not enough radiation, so it was like below your flux. It may happen that at the same time or at times compatible with LISA, these will go up. So it will appear as sort of a rebrightening, though technically is not a rebrightening due to the presence of massive black hole binaries that produce a cavity. But for you, it still looks just simply as an increase of the luminosity in X-ray as function of time. So that type of emission, yes, it can be mimicked by an AGN, let's say. So I will move quickly to the last slides, also because it's the last afternoon, so I guess you're all tired. And still connected to this point, the fact that let's suppose that LISA gives you like an error box, you point your telescope and you detect some flux coming from that. Like your telescope has a field of view of 0.2 degree, okay, so you detect it from there, and now you're interested in actually understanding which galaxy hosted the massive black hole binary. So a key information here is that the fact that you detect the electromagnetic counterpart is different from the identification of the host galaxy. And actually, the identification is a much more complicated issue. And you can see it here. So, for example, here you are looking at the this is like the number of potential host galaxies in LISA sky localization as function of redshift, and like for system of 3 times 10 to the 5, 3 times 10 to the 6, and 3 times 10 to the 7 solar masses. And as you can see, the typical sky localization of LISA will not contain just the galaxy hosting the massive black hole binary merger. It will contain many more others. So for example, if you look at this, you can clearly see that, let's look at the merger case for simplicity, okay? So at merger, you still have, at redshift 1, for example, you still have 100 on average. This is like average estimates, and like the error bars that you see here is like the vertical line here are the error bars. The typical sky localization provided by LISA is still containing hundreds of galaxies, which means that identification is going to be very challenging. We have a question.
It's just about the y-axis. Is it normalized with respect to 90?
Sorry,
like, is 1 on the y-axis 90 or 1? I'm just like, what's the n subscript 90?
It's like the number of galaxies in the 90% error volume provided by LISA.
Okay, so the 1 is a 1. Okay.
And about what can also mimic the emission from AGN, here on the right, you can see instead the number of possible transients that will appear in the same sky localization provided by LISA. Here, transients is, in this paper, they were looking at like transit from core collapse supernovae, gamma ray burst, and other processes. And let's say that if you want to be a bit more optimistic, you can look at the blue lines. So the blue lines means that you are, with redshift, for example, in this case, means that you are able to get the redshift for all the galaxies, actually, no, for all the transits that are in the LISA sky localization, which is an overestimate, of course, because this will never happen. So if you want to be a bit more so if you want to be optimistic, you look at the blue one. If you want to be realistic, you look at the orange one, let's say. But typically, you can see that just focus at 1 hour before merger, because this is like where typically we have indeed the merger. We might expect still a lot of transient, especially between redshift 0.8 and redshift 2. Which means that indeed the identification of an electromagnetic counterpart is probably going to be very challenging for the context of LISA. And I think that I'm done. So final remarks is that, yeah, as I said, multi-messenger is an interesting science case, but is indeed very challenging. Something else that I would like to mention is that, and that I don't think maybe is often appreciated, is that multi-messenger is probably the only science case of LISA that is time sensitive, in the sense that most of the LISA analysis, you can do it a posteriori. But multi-messenger, due to its nature, so due to the fact that you want to catch an electromagnetic counterpart and that the electromagnetic counterpart will disappear soon, is the only science case that is indeed time sensitive. And this means that we really need to work hard, also on the side of low latency, of course, in order to maximize the scientific outcome. And with that, I'm done. So thank you for your attention.
Thank you very much. So especially to reassure us about the need for low latency. Are there final questions? No? Well, let's give a round of applause again to Alberto.